Hello, everyone, and thank you for joining us. I'm Walter Schnapp with Trillion Quality Systems. I'm here with our supporting partners in the southwestern U.S. So today we want to talk about scanning and specifically automation and scanning. So in today's fast-paced manufacturing environment, whether you're in aerospace or automotive, medical, time is one of your most valuable assets. So we're going to be looking at a way to reclaim that by moving some of these processes to automation and moving from manual data capture to a semi-automated precision capture. So real quick, I just want to give you a little bit of background about Trillion as a company. So Trillion Quality Systems was founded in 1998 by our founder, John Tyson. Our primary headquarters is located at the King of Prussia office outside of Philadelphia, but we do have satellite offices all over the country. The Great Lakes office is another one of our primary ones, as well as the one in Seattle. So at Trillion, our footprint spans the most demanding industries, from aerospace and defense to automotive and medical device manufacturing, materials. We try to help our customers solve their most complex engineering hurdles with a variety of different tools. All of our optical metrology tools are completely application agnostic. We really don't care if your material is metal, composite, biological, if the environment is a clean room or a high test heat cell or a pad for a engine test fire. It really doesn't matter. We will still be able to offer really valuable insights with our methodologies. Success in 3D metrology is certainly something that comes with a learning curve. Trillion really sees itself as a complete partner in this space, and we support our customers in several different ways, one of which is with systems and hardware. Through our partnership with ZEISS, we're able to bring the most advanced sensors in the world to our customers' workspaces. So besides this, we also have our engineering services. In this case, a Trillion engineer will actually come on site with a measurement system, or they can use the customer's measurement system and actually make the measurements on behalf of the customer and then provide the insights in a report with the data afterwards. This is a really useful setup for customers who are new to optical metrology and don't have the insights and the training yet to get to the point where they can do it themselves. And then the other way is with training and education. We really believe in empowering our customers as much as possible, everything they could need to be able to get the most out of their systems and get the quality data and insights that they're looking for to help them solve their problems. So ZEISS has a very wide range of optical metrology-based tools. Today, we're going to be mainly focused on the scanning portion, but there are other areas that we focus on at Trillion. Aramis being one of them, that is the optical strain measurement technology. Argus and Tri-Top are both DSLR-based technologies. We see Argus used a lot for sheet metal forming analysis, so often in the automotive industry. Tri-top is an optical CMM where you're creating a large point cloud through a large amount of images taken from different points with the camera. And then CT scanning is an area that ZEISS is very active in. They come from large volume to very small volume, so it just depends on what the application necessity is. So the sensor that we used for pairing with the ScanPort was the ATOS Q 12M sensor. This is the spec sheet. ZEISS also makes the ATOS Q 8M version. Both are going to be excellent scanners for the half meter and under volume. So for the demonstration, we're going to be using three slightly different Artemis capsule models. Each was 3D printed with geometric variances from the others, so as to highlight the system's capability of differentiating those with the scanning. With the capsule secured on the platter, we can initialize our measurement series in the software. So as the sequence begins, the ATOS Q projects high-resolution blue light fringe patterns onto the part. The software automatically tracks the table's position using the integrated reference points. So it's stitching each individual measurement into a global coordinate system in real time as it's doing this. So once the automated rotation sequence finishes, the software is just going to process the raw data and it instantly stitches all the individual views in together to this clean, high-resolution gray mesh that you see on the first capsule. So viewing the part as a shaded gray mesh allows us to visually inspect the quality, and you can see how cleanly the Q captured all of the geometric details. So all in all, not a bad scan. So with just the pairing of the rotation table with the scanner on the tripod, with basic automation, you have a great measurement coming out of that. But in order to get into the higher efficiency and more of a higher throughput workflow, we want to bring in the ZEISS ScanPort. So this is a new tool that they have introduced. So this is a compact semi-automated system, and it brings a three-axis desktop automation directly into the workspace. So by combining the motorized rotation table and the motorized arm on the scan port, the arm moves up and down, it tilts, gives you the full three axes of motion. It moves the sensor to basically to pre-program distances and angles automatically, and completely removes the need to manually build fixtures or angle the part that's being measured. So before introducing the first part to the workspace, we're going to create a coordinate map with the reference targets that are on top of the rotation table. So the scan port automatically executes a three-axis motion path. So it moves the sensor through optimized tilt angles and heights. By scanning the empty table first, the system identifies and registers the exact spatial coordinates of each of the reference targets without any obstructions from the part. Once we have all of the scanning completed of the three parts, we can begin to bring the meshes into the inspect space. So we'll just do that now with the STL files for each of the individual parts. So once the import is complete, the software designates the master STL file as our nominal baseline. And so with our reference data and all of our scan components successfully loaded into the same project workspace, we're ready to move directly into the part alignment. So with the alignment locked in, we can visualize the geometric differences between our scan part and the other CAD. So with our best fit alignment locked in, we can visualize the two meshes overlaid on each other. And now we can begin to add our deviation labels to the surface points of interest. So once we've completed all of the different inspections that we want to perform on the different meshes for the scans, we can then move into our reports workspace. So the reports workspace environment allows us to document our data and structure our findings into a really professional presentation ready format. Makes things a lot easier when it comes to that portion of the project. So here we have the arranged color inspection maps of all three unique capsule models right next to each other on a single page. So if this was a real project, we would be ready to submit this for review and feedback. Now that we've covered the topic of the ATOS Q used with the ScanPort for automated scanning processes in that context, let's talk about the T-SCAN Hawk 2. So this is a handheld laser scanner that was brought to the market by ZEISS. It's designed as a portable handheld 3D laser scanner, rated in volumetric accuracy down to 0.02 millimeters. This is a wired connection, but the weight of the sensor itself is under a kilogram, so it's very easy to move around as for portability. So the Hawk 2 has a couple of really interesting features in that it is capable of doing photogrammetry, and for that, included is a pair of scale bars. Also is the calibration object standard that is used for calibrating the sensor itself. So the calibration process is very straightforward. It's 8 image sequences that you take with the different positions. It's not possible to calibrate incorrectly. It won't allow you to progress to the next step in the software. It's one of the really great benefits of working with ZEISS tools is that the calibration is very trustworthy. So to get further into the details of the T-SCAN Hawk, I'm going to bring Jerem Hatch on, who is one of our senior applications engineers for the West Coast team.
For this next section, my name is Jerem Hatch. I'm a senior applications engineer working with Walter on the West Coast, and I will be giving a hands-on demonstration using the ZEISS T-SCAN Hawk 2 in the ZEISS Inspect optical 3D software. First, with a new instance of ZEISS Inspect Optical 3D open and with the T-SCAN Hawk 2 plugged in and powered on, I will first check our connection. Next, I will start a new project, and as you can see, the software automatically opens the T-SCAN Hawk 2 workspace on the left side of the screen. The back of the T-SCAN Hawk 2 has 4 physical buttons that can be pressed to navigate through a predefined kiosk mode. To initiate the kiosk mode, I will initially press the right arrow button while in the new project. This mode simplifies much of the software interface and starts to guide the user through the scanning process. Using the arrow buttons on the back of the unit, I'll start by selecting the type of scanning template. In my case, there are no reference points on the propeller sample itself, but there are points around it, which we will use for the scan. You can see some of the other options, including something called satellite mode for large parts. I can also choose the initial point spacing that will be used for the scan mesh. Choosing this template, we can see new options available, including the option to use the hyperscale bar included with the system for a quick recalibration if needed. We need to capture our reference points, which are the points currently on the rotation table and on the monuments around the propeller. I'll enter the current temperature of the sample and click the trigger button once on the T-SCAN Hawk 2 to initiate the point cloud scan of the reference points. You can see that the T-SCAN Hawk 2 projects 2 laser lines that overlap to form a cross when at the center of the measuring volume. This is the distance at which you will typically scan. Once I collect all the points, I can click the trigger button again to stop and the right arrow to save that point cloud. I'll then be prompted to define a background plane, and in my case, the reference points on the turntable will make a nice plane to define where my scan area should stop so that I limit the amount of background data captured by the scan. Next, I'll move into scanning, and here you can see a few different options, one for exposure mode, which has a default setting, one for dark or shiny surfaces, and another for bright surfaces. Next is the projection mode, which is typically set at default for surface scanning and also includes an option for deep pockets such as through holes for bolts or other cavities. You are typically able to use this tool to scan depths of about 3 times the diameter of the opening. The last option is the dynamic camera, which gives you live visual feedback of where your T-SCAN Hawk 2 is looking relative to the position of the part. Next, I'll move up to scan, and when ready, I'll press the trigger button again once to begin scanning. You can see the laser projection lines of the T-SCAN Hawk 2 and the current state of the mesh in the live view of the software. I'll move the T-SCAN Hawk 2 slowly around the part, building up my mesh until I have the appropriate scan density that's required for my analysis. You can see a few scanning artifacts from the background are still being picked up. Once I complete my scan, I will trim those out of my project. Now I'm going to use the Deep Pockets projection mode to try and get some more scan coverage inside of the attachment hole of the propeller. Once I'm happy with my scan, I can use the right arrow on scan to finish. And here you can see I can either choose to scan the opposite side of this propeller, resume my current scanning process, redefine my background plane, or finish the scan. I'll go ahead and finish my scan, and you can see I have the option for post-processing this mesh, polygonization, with a few different options. Here I'll use standard, and I'll choose to fill any of the reference points locations with mesh data. Once the polygonization is complete, I can again scan another side, resume scanning the initial process, redefine my background plane, or continue with the inspection in the software. Once I return to the software, we're now in the inspection workspace where we can do comparisons to CAD data. We can look at cross-sectional geometry, create geometries such as fitting planes or fitting cylinders. But in my case, I've noticed that there are some finer details on this propeller that have not been captured with the initial mesh point spacing. But first, I'm also going to trim out any of the erroneous mesh data that was picked up from the background during the scan. To increase the detail of my scan in certain locations, such as for the serial number or the logo of the propeller, I'm going to go back into the T-SCAN Hawk 2 workspace, and I'm going to choose this button here for Scan Details, which allows me to decrease the point spacing by a certain factor, and also select the area of which I want to rescan at that higher detail, and then begin scanning. Here again, I can choose exposure modes and projection modes, and I'll just bring the T-SCAN Hawk 2 back into position, press down on the trigger once, and begin scanning and filling in that area with higher resolution data. Once I'm done, I'll go ahead and click Finish. Now you can see some of the higher details that were missing from the initial scan that I was able to go back and scan in finer detail. To finish up this project, I'll polygonize the mesh, and now you can see the nice polygonized mesh here showing off some of the raised lettering on the surface of the propeller that I was able to capture with the finer detail portion of the scan.
So many thanks to everyone for attending today's webinar on scanning automation using ZEISS tools. So the value of adding automation to these systems centers a lot on precision and consistency. So by automating these measurement paths, you're removing operator error, accelerating inspection cycles, and you're ensuring repeatable data collection directly into your quality management systems. So it's very valuable in that sense. So to explore more into how these would fit into your specific applications, we can now begin the Q&A portion of the webinar, and we'll get into the further details. So if you want, you can please begin to submit your technical questions into the chat panel, and we'll get into that side. Thanks.